for the final talk of the session, we'll have Yuxiang talking about compression of shallow circuit states.
Yeah, thanks for the introduction. And Yuxiang from the University of Hong Kong. And today I'll be talking about my recent work on compression of shallow circuit states. As you can see, there's no learning in my title. And actually, I'm not sure why they placed my talk in this learning session. But so since I'm already here, let me try to motivate with two questions related with learning. So the first question is that if you want to do information storage, if you want to store quantum information, can we do it as efficiently as we learn? The second question would be, then can we even store quantum information by using learning? Okay, these are two fundamental questions that seems to be quite interesting. And with this, I'll try to answer this with the main result of this paper. So which is that consider you have n copies of some unknown m qubit pure states with a guarantee that they are generated by some one-dimensional brickwork circuit of constant depths. This is what we call shallow circuit here. So you have n copies of some unknown state generated by shallow circuits. And we know two things. One is that there exists some compression protocol that compresses this n copy state into a hybrid memory consisting of quantum bits and classical bits of size of order m times log n. So compared to original cost, which is m times n, you get an exponential compression in n. And the compression protocol is phaseful, what I call phaseful, which means that you can recover these n copies up to some small error that vanishes in n. The second thing we know is that any attempt to compress this state into a fully classical memory cannot be phaseful, cannot have vanishing recovery error. So with this, what would be your answer to these questions? Okay. For me, like the answer to the first question is at least in some sense yes, at least in leading order, because this result gives the compression result gives the efficiency of information storage. And somehow, what is the efficiency of learning then? Well, if you have n copy states, then the efficiency of learning is bound by the standard quantum limit, which means that the mean square root error would vanish as 1/n. And this converges to 1/2 log n bits per degree of freedom per free parameter you have. And for this kind of shallow circuits we consider, the number of degree of freedom is proportional to the number of qubits m. So that's, you get really matching order. So that's the answer to the first question. The second question would be no, because apparently if you attempt to store quantum information, if you could store quantum information by just learning them, then essentially you are contradicting this result by showing that you actually have a way to sort of compress these states into fully classical memory, because by learning, you're collapsing the quantum states into fully classical bits. Okay, so with all this, let me get into a bit more details. So let me briefly remind you what task we are considering. So we consider compression of quantum states, which means that we want to encode some unknown quantum state rho drawn from some given set S into some memory M. And we would like to recover this rho, of course, up to some tolerable small error. And our goal is to design some compression protocols consisting of encoder and decoders, which are CPTP maps that are independent of the input state. So we don't know what the state is. And in this setting, it's sometimes called a blind setting of compression. And our memory cost is quantified by log of dimension of m, which corresponds to the number of bits or qubits you're using. And we focus on n copy states. So our input states are of form rho tensor n. And we require the protocol to be phaseful in the sense that the trace distance between the output states and the original n copies must vanish in terms of n. Under this restriction, we ask the question, how could we minimize the memory cost? How could we minimize log of dimension? Okay, that's it. And notice that we consider the state we are compressing are of the form rho tensor n, so which is not IID state, so it's different from the sort of Schumacher compression or Shannon compression you're sort of more familiar with. But why do we consider this new type of compression? This has to do with learning / metrology, because they are the n-copy states are sort of natural resource in metrology, let's say. Because, for instance, in metrology, you want to learn some physical parameter theta. And what you do is to prepare some proper probe state and pass them one by one into this physical process. Okay? So what you end up with is exactly many copies of some state rho theta, which is partially unknown. This corresponds to our setting. Moreover, the quantum Kramer bound in metrology is attained when you have many, many copies. So that's also motivates why we study the asymptotics of large n. And even more, if you want to attain what is the ultimate limits, the high-level Kramer bounds, it in general requires you to perform some collective measurement on this rho tensor n altogether, so you cannot use individual measurement. So in this case, there's need to store some generated copies and using potentially compression. And this n-copy state compression even leads to some new paradigms of sensing and learning and metrology beyond that. For instance, if one has a certain quantum network of sensors, you may think of a center who want to collect data from remote sensors. And in this case, you use some remote, you have to use some quantum channel to communicate these probes. If you have compression, you save the critical quantum memory. And if you think of some other task, it could even bring some quantum advantage. For instance, if you want to estimate the total duration of some discrete events, we showed in a prior work with Julie Kilibella and Masahiro Hayashi, who is in the audience, that you can actually, with this compression, you can design a sort of cool quantum stopwatch that achieves some new quantum advantage. There are more motivations beyond this in information theory, in mathematical physics, and in foundations. Okay, so now enough about n-copy states. Why do we particularly interested in shallow circuit states? Well, for this, let me briefly review the literature of n-copy state compression. So this task of n-copy state compression has been done for pure qubit states, mixed qubit states, some classical systems. And in the QIP, maybe 7 years ago, I presented this work, this general result on optimal compression of d-dimensional mixed quantum states. So we have the optimal protocol for that. So it seems already general enough. But why do we still, is there any limitation of this? Well, a general feature of all this is that they have to assume, this result have to assume the dimension of each system you want to compress to be fixed and negligible compared to the number of copies. And this is more matching the setup of metrology, where you have some fixed dimension physical systems, and you're interested in improving the accuracy of estimation with respect to the sample complexity. But here at QIP, we're more and more interested in what is called quantum learning in the computational setup. Actually, it took me a long time to figure out what the distinction between these two fields are. But as far as I understand, in quantum learning, you are more interested in what is the trade-off between the system size and sample complexity, fixing the precision somehow. So you consider learning really outputs, for instance, of some large quantum computer. And in this case, you can see the previous result does not cover this case. Moreover, the existing tools somehow have to assume this system dimension to be fixed and negligible, and therefore cannot be brought over to this new setup of learning. So in order to have compression for learning and computing, we need to particularly consider some compression from structures. So we have a large dimensional system, but somehow with some nice structure, so the number of free parameters in this structure is somehow small compared to the dimension. And shallow circuit states is a nice candidate of it. It's a very large dimension, exponential in the number of qubits, but somehow the degree of freedom it has is limited because of this shallowness. Okay? Beyond this technical reason, there are good motivations with shallow circuits themselves. They're a hot topic because, for instance, you can show some unconditionally more quantum advantage compared to their classical counterparts. And if you're doing, on the applicational side, if you're doing a near-term quantum computation with some noisy device, you're pretty much dealing with shallow circuits. So there have been a lot of interest in, especially at QIP, with shallow circuit states. Most research focus on sort of learning of shallow circuit states, as you have heard from this QIP as well as last QIP. But learning is an important task, but it's sort of incoherent in a sense, because you collapse all the quantum information to extract something from it. Okay? So we'd also like to see something that is coherent, where you are forced to preserve the coherence in quantum states. And compression would be a nice candidate. Okay? So with this, let's move on to more details of the compression protocol. Be reminded, we consider compression of n copies of some shallow circuit states, and we require the compression arrow to be vanishing in n. So the performance of compression is like this. So if we assume that n grows fast enough, then we can design a computationally efficient compression protocol that sends this n copy state of some shallow circuits into a hybrid memory consisting of both classical bits and quantum bits. As you can see here, that in the leading order, both classical and quantum costs scales as m times log n as promised. You may still be a bit puzzled, why do we have hybrid memory? Why can we use hybrid memory instead of fully quantum memory? I'll tell you more about this very soon. So, but let's remark that also like this sort of m times log n rate is optimal. We can prove this using some counting technique. So we can show that any faithful protocol will require this number of qubits/bits at least. Okay? So with more observation, you can see that we compress some n copy states, which lives on m times n qubits into a hybrid memory of size m times log n. So we achieve an exponential compression in terms of the number of copies, which are referred to as more classical parameter, and they're compressible because they correspond to the classical limits of learning. And somehow you also see that this qubit number m is not compressible. So we have originally m times n, now we have m times log n. So in terms of m, is not compressible because this m corresponds to the number of quantum features in the shallow circuits. And in this sense, these features are not compressible. Another curious observation is that if you look at the ratio between the quantum and classical costs, you can see that it vanishes for large enough n. So this somehow should suggest, in a sense, suspiciously, that the quantum memory cost is negligible. Okay? So then as learning experts, you might be tempted to ask, can we just compress by learning? So if you have n copy states with large n, you can learn the state really well. Okay? And this is good news for you, but not for me, because then this trivializes this whole thing, and the best way to compress would be to learn. Okay? But the caveat here, the catch here is that we would like to recover n copy states, not just one copy. We would like to recover all these n copy states. If you do full tomography on these n input copies, you are left with some standard quantum limit error 1 over root n, and they add up. So somehow you wouldn't get vanishing arrow if you consider n copy distance with original states. And even more, we can rigorously show that any compression protocol for these shallow circuit states attempting to use fully classical memory would not have vanishing arrow, no matter how large this classical memory is. Even if the classical memory is infinitely large, you still cannot work. Okay? The proof is based actually is an extension of our previous result, which I presented at maybe 7 years ago at QIP as well. So this reveals a nice thing on data structure of n for quantum states. So if I have n copies of some quantum states, it looks more like very long classical documents plus some short but necessary quantum signature. So without this quantum signature, you cannot recover the original n copies. Okay? With the remaining time, let me just attempt to tell you a bit in high level this idea of the compression protocol. Okay? So we make several observations. The first easiest observation is that if you have n copy states, pure states, then they live on the symmetric subspace. Okay? So this somehow suggests that we can already compress by just sending them into the symmetric basis. Okay? This would work, for example, if you have small dimension system, if the dimension of systems are small. But it doesn't work if in our setup, we have a very large individual dimension. In this case, the symmetric subspace themselves would be too large and too empty, have too high degree of freedom. And our solution is that we should find the hidden corner of this symmetric subspace to hold that is still enough to host these shallow circuit states using the structure of shallow circuits. Okay? So we are not considering any M qubit state. We're focusing on a particular set of states with certain structure, and therefore can pick this small corner of symmetric substance. But how this can be done? Well, another observation is that this is a mathematical result showing that if we know that the shallow circuit state is living, if we have enough information about these states to determine vanishing a small neighborhood to contain these shallow circuit states. So before that, you have some input state, you totally have no information about it. But if you can acquire enough information to pin it down to some small neighborhood, then there exists some quantum operation transforming n copies of this state into some multi-mode coherent states. Okay? So the remaining uncertainty about these states would be transformed to uncertainty about like the amplitude and phase about coherent state. This result for fixed dimension is known as the quantum local asymptotic normality and has been extended here a little bit to growing dimensions. Okay? And once you have these coherent states, compression is easy because the coherent state has some uncertainty in the phase and amplitude, but we know also we have some information about the energy of it. Then we can just give a truncation on it. Coherent state's photon number distribution follows Poisson distribution and therefore has certain concentration phenomena. And if you just truncate on this, then you're left with most of the information. So it just can compress coherent states via truncation. Also, the number of modes of this multimode coherent state would be proportional to the degree of freedom of your small neighborhood. So if we have a low degree of freedom neighborhood, then we have a very efficient compression. Okay? So the gap between these two can be bridged in the following way. The first is like a third idea, we shall call an idea of gentle tomography. So this is actually a tip for you, no matter what kind of information processing you're doing. So even if you're just learning states or you're cloning states, as long as you're given n copies of some completely unknown quantum states, you can always peep into it without losing anything. This means that before your exam starts, you can kind of, cheat a bit looking at the state and without losing anything, without being caught. Okay? What does it mean? It means that if you have a lot of copies, you can just pick up many states, but as long as the number of states you pick is negligible compared to the total number you have. For instance, if you have 1 million copies, you can pick up 1,000 copies, and what you do is to do some tomography on it. You destroy all these states. This gives you some good estimate, pre-estimate of what the state is. Okay, so this fixes your state into a vanishing neighborhood. But you lost some copies, right? But I promise you can do this for free. Then how is this achieved? Well, you can just apply quantum cloning on the remaining copies. Approximate quantum cloning will give you back these missing copies with some fidelity going to 1 as long as the number of copies missing is negligible compared to the original copies. Okay, so you can always do this. This gives you a vanishing neighborhood. Okay, very good. So are we done yet? No, because, okay, another remark is that why we have hybrid memory before. So as promised, I answer you now. Like, this is because we did this tomography step. And for tomography, you can store the outcome using bits. So that's why we have a hybrid memory of bits and qubits. We use this gentle tomography to convert the memory cost into classical bits. Okay? So we are not done yet, as said. Because from tomography, what you learn is that your shallow circuit states is epsilon close to some known states, the outcome of your tomography. Okay? But somehow this means that there exists some M qubit unitary taking your unknown state to this known state. But this unitary has exponentially many degrees of freedom. You don't have any structure about this unitary. So this is missing another requirement that this neighborhood must be of low dimension, of low degree of freedom. To achieve this, we need to find another unitary W, which is also small, close to identity, and which can be described using order of M, some free parameters. And this step is actually highly non-trivial, but due to time limits, I don't have time to tell you about this. So, but once we have done this with the help of shallow circuit structure, we can achieve the whole compression. Okay, that's pretty much the idea. With this, maybe I'll just skip the summary and outlook and use the remaining maybe 1 minute to do some advertisement. First is that we always have, I always have positions in my group. So if you're interested, you can check out the website. The second is that we are hosting in Hong Kong a big conference this summer called AQUIS, which is like pretty much Asian version of QIP. And this, we are expecting maybe like 500 audience, almost maybe slightly more than half of the size of QIP. So this is going to be a big event. Moreover, beyond this scientific reason, Hong Kong is a lovely city, which is very accessible. You have a lot of flights internationally, and it's visa-free for most countries. And also it has a subtropical warm weather, and we have good food, okay? That's very important. With this, I would like to conclude my talk here and thank for your attention.
Are there any questions?
For the moment, we are focusing on pure states. I mean, intuitively, you should be able to do mixed state. If you have a bit noise on these shallow circuits, I think you have the same thing, but technically there's some thing that I could not really tackle. So for the moment, we're restricting to pure states. Yes.
Does your result have anything to do with like recent work on learning shallow circuit?
Yes, I think it's somehow you have to pick some. You can pick your favorite way to do tomography, but of course, if you just use some general tomography approach for generic states, you don't use this nice recent work by Robert Huang and others. So then maybe the computational efficiency of your protocol would not be good enough. You'll still be, from information theoretical perspective, there's no difference. But somehow, if you use their result, this gives you a nice structured estimates of the shallow circuit states, and also it is computationally efficient. So this will be the best way here so far. Yeah.
Thank you.
Thank you.
If there aren't any other questions, then let's thank Yuxiang again.